Today, let us discuss about the different styles of writing the Verilog program. We can write the Verilog program at four different levels. At the switch level, the basic level, where the circuit is described with the help of transistors. Next is the gate level, where the digital circuit is described at the gate level using the gate instantiations and the data flow modeling, where we are going to describe the particular logic with the help of the logical expressions and the behavioral level, which is the highest level of describing the Verilog, where we are going to describe the program with the help of its truth table. So when we are going to see, here we are going to have the circuit diagram of a simple inverter with the input as in and the output as out. So when we are going to see the circuitry, this particular inverter logic or nothing but the NOT gate is described at switch level, where these two transistors Q1 and Q2 acts as the switches. So we are going to have the upper transistor and the lower transistor. Both the upper and lower transistors are of NMOS transistors, whereas the transistor Q1 is operated in the enhancement mode and the transistor Q2 is operated in the depletion mode. So depletion MOSFET is always in on state, even we are not going to apply any voltage between gate to source. So VGS is shorted here. And coming to the enhancement MOSFET, when the input equals to 0, in equals to 0 volts, then the transistor Q1 goes into off state. And since the upper transistor Q2 is always in on, because of VCC we have applied, the current flows through VCC, through the on transistor and to the output terminal, making the output as logic 1. So when input equals to 0, the output equals to logic 1. Similarly, when the input equals to logic 1, then the enhancement MOSFET Q1 goes into on state because its gate to source voltage is positive. Nothing but logic 1. So since the lower transistor is in on state, whatever may be the output voltage, it tries to pull down towards the logic 0, making the output voltage as logic 0. So when input equals to 1, output is 0, and when input equals to 0, output equals to 1. So this simple circuitry can be used as a simple NOT gate, also called as an inverter. So describing any logic with the help of transistors, we can call this model as the switch level modeling. Coming to the gate level, we are instantiating the gates, the primitive gates, and then writing the program. Here, when we are going to see this diagram, nothing but it indicates a 2-input AND gate, and the output C is nothing but A ANDed with B, A ANDed with B. So we are describing the program by instantiating the AND gate here. So like this, if you are going to write the program at using the gate instantiations and primitives, we can call it as the gate level. Coming to the next level of describing the digital circuits is nothing but the data flow modeling, where the logical expression is important. Here, the logic expression is given as y equals to AB plus CD. Means the AND operation is performed between A and B and also between C and D. So AB and CD are odd together and the whole output is assigned to the output called as Y. So here we are describing the inputs and describing the outputs. Using some symbols, you are writing the program in the data flow modeling. The keyword that we are going to use in data flow modeling is assign. By using the keyword called as assign, we are assigning the values onto the of the right hand side onto the left hand side. We are assigning the logical expression which is there in the right hand side and that value is assigned to the left hand side. So this is about the data flow modeling, where the logical expression plays a key role in describing the program. At last, the last highest level of describing the program is the behavioral modeling. Simple programs, for writing the simple programs, we can use the data flow modeling, but when the program complexity goes on increases, just like repetitive operations are required, then we can go for this behavioral modeling. Means we can include the looping constructs, we can have the branching. So just like in C programming, we can use this particular behavioral model. So if you are going to see an example here, the E is the output, which is nothing but here you are going to have AOI logic, and AND operation is performed between the inputs A and B and C and D, and then they are ORed together, and a complement is applied to this particular logic. So first AND operation, then OR operation, and then an inverter operation. Nothing but it's a AOI logic. After performing this AOI logic, the output is assigned to E. So means this particular operation is performed based upon the condition. Here we are going to have the conditional statement which can be used in the behavioral model. If the condition means, what is that condition is, if at all there is any change in A, B, C or D, then only the operation is being performed, which is there on the right hand side, and that result is applied to the left hand side. So in this way, you're writing the program where you can use repeat statements, you can use if statements, you can use the case statements. All these comes under the behavioral modeling, which we are going to see in detail further. Coming to the general concepts that we are going to use in Verilog: concurrency. Sequential and concurrent. Sequential means one after the other. If the operations are performed one after the other, then we can call it as sequential. If the operations that are performed, operation of statements that we are going to use, if they are run parallelly, then we can call it as concurrency. So the terminology called as simulation. Simulation is nothing but applying a set of inputs and verifying whether you are going to get the exact output or not with the help of truth table. That we are going to call it as a simulation. Giving a set of inputs, we can call it as the test vectors. So these test vectors applied to the circuitry and then verifying whether we are going to get the exact output or not. So this we can call it as the simulation. Coming to synthesis. Synthesis, it's a tool where whatever may be the program that we are going to write in the form of a language, it is converted at block diagram level, in turn at the gate level. So this particular conversion from the abstract level, nothing but at the description of the program in the form of a language, is converted into the block diagram level, and in turn at the gate level, this is done by the synthesis tool. So functional verification. We are going to have two verifications in digital logic. For any digital logic, we can do two types of verifications called as functional and timing verification. Functionality means whether the truth table is satisfied or not. For example, if you are going to take an AND gate, we can verify the AND gate by applying the inputs, and when according to the truth table, when both the inputs are ones, then only the output will be 1. In rest of the cases, the output equals to 0. So like that, if you are going to check each and every combination of inputs are applied to the circuitry and then checking the output, then we can call that as the functional verification. Nothing but simply we can say that checking the truth table, nothing but the functionality comes under the functional verification. Whereas timing verification, it also plays a key role in verifying any digital logic. So, at what instant we are going to get the inputs, and at what instant we are going to have the outputs, that comes under the timing verification. So, which plays a very crucial role when there are more number of blocks and one block is depending upon the other. The timing instant of the result of one of the block depends upon the other block. So timing verification is also very important. Coming to system tasks, there are many system tasks that are used in Verilog. Just let me give some examples like the dollar display, dollar monitor, which are used to control the particular actions that are taken place while we are going to execute the program.